Dear students, today we are going to discuss Galilean transformations from the Unit 1, Non-Inertial Systems and Fictitious Force. Suppose a physical phenomenon or event is observed from two separate reference frames. They'll have two separate sets of coordinates corresponding to their frames of reference. In such cases, we need equations relating the two sets of coordinates of events in the two frames. These equations relating the two sets of coordinates of the event in two frames are called transformation equations. If the two frames are inertial ones, then the transformation is referred to as Galilean transformation. There are three types of Galilean transformation equations: Galilean coordinate transformation, Galilean velocity transformation, Galilean acceleration transformation. First, let us look what is Galilean coordinate transformation equations. Suppose let us consider two inertial frames of reference, S and S dash. S is at rest, S dash is moving with a uniform velocity v in the positive x direction, and let t and t dash be the time of an event measured by the S and S dash. Let us consider two observers, one in S and other one is S dash. To begin with, the two frames coincide at t is equal to t dash is equal to 0. So they are having the same origin, t equal to t dash is equal to 0. After some time, the two frames observe an event taking place at a point, let's suppose P, and the coordinates of this space coordinates of this point P is x, y, z, comma t, and this is with respect to the rest frame S, and with respect to the moving frame S dash, the coordinates of this point where the event occurs can be considered as x dash, y dash, z dash, and t dash. So this x dash, y dash, z dash, and t dash corresponding to the with respect to the moving frame S dash can be written as x dash is equal to x minus vxt. Vx means this in the velocity is measured in the positive x direction. So x dash is equal to x minus vxt. Since there is no motion along the y and z direction, we can write y dash is equal to y, z dash is equal to z, and we already told this same event occurs simultaneously for the two observers. So t dash is equal to t. This set of equations are called Galilean transformation equations. These are Galilean coordinate transformation equations. So next we need to obtain Galilean velocity transformation equations. Before that, Galilean transformation equations can have the inverse transformations. If the inertial frame S is moving with the velocity v along the negative direction, negative x direction, with respect to the S dash, suppose S is moving with the velocity v along the negative direction of x-axis with respect to S dash frame, then there is a set of equations, transformation equations. They are x is equal to x dash plus vt, y is equal to y dash, z is equal to z dash, t is equal to t dash. The direct transformation equations can have the inverse transformation. Then this set is known as Galilean inverse Galilean transformation equations. Inverse Galilean transformation equations are as seen here. Now we are going to obtain the Galilean velocity transformation equations. This is obtained by differentiating the Galilean coordinate transformation equations with respect to t. So we will obtain the equations as u dash x is equal to ux minus v, u dash y is uy itself, u dash z is equal to uz. So the inverse of these velocity transformations are as shown here. If you want, I can work out how these equations are obtained. That is, it is obtained from differentiating with respect to t. So let us differentiate dx dash by dt. So dx by it is equal to dx by dt minus v. So this is the differentiating the equation 1, the previous coordinate Galilean coordinate transformation equation with respect to t and t dash. So we are differentiating with respect to dx dash by dt dash, and it is equal to dx by dt minus v. D by dt, we can write d by dt dash is equal to d by dt. This is same because t dash is equal to t, and similarly the other equations dy dash dt dash can be written as dy by dt, and for the x dash z dash we can write dz dash by dt dash is equal to dz by dt. So we can write here, we can write so this I will wipe out this. We can write dx dash by dt dash is equal to u dash x. This is x component of velocity measured with respect to s dash, and so the equations for velocity coordinates or velocity transformation equations, we can write ux dash is equal to ux minus v, uy dash is equal to uy, and uz dash is equal to uz. So these are the velocity transformation equations as we obtained here. So inverse velocity transformations are as ux is equal to ux dash plus v, uy is equal to uy dash, uz is equal to uz dash. So these are the velocity transformation equations. If we look for the Galilean acceleration transformation equations, we can obtain ax dash is equal to ax itself, a dash y is equal to ay, a dash z is equal to az. This is because we are obtaining from differentiating the equations, velocity transformation equations, again differentiating with respect to t, since t is equal to t dash, and we can obtain this equations because dv by dt is equal to 0. So again we will get a dash x is equal to ax itself, a dash y is equal to ay, and a dash z is equal to az. It shows that this both frames measures the same acceleration. So according to Galilean transformation, the acceleration of particle is same for all observer in all frames in uniform relative motion. So this acceleration remains in invariant under Galilean transformation. So acceleration is called Galilean invariant physical quantity. In general, any physical quantity which remain invariant under Galilean transformation equations are called Galilean invariant quantities. So let us check whether this Newton's second law is same in two different frames, reference frames. So for that we put one observer in the unprimed frame S, and the other in the primed frame S dash, moving with the velocity. So relative to S frame, we are considering this Newton's second law, or we are checking whether force is invariant under two different frames, reference frames. For that, f dash is equal to m dash a dash, or a dash can be written as d square x dash by dt dash square, and from this we can see that the f dash in the measured in the primed frame or s dash is same as that measured in the unprimed frame. This gives us Newton's law. Second law is invariant in under the Galilean transformation. So this Newton's second law or force is also as acceleration is Galilean invariant physical quantity. We can check a physical quantity whether it is invariant under most of general physical quantities which remain invariant is under Galilean transformation equations are called Galilean invariant quantities. So Newton's second law we have checked. Another point we want to discuss is uniformly accelerating systems, or it is called non-inertial frames of reference. A frame of reference which Newton's laws are not valid are called non-inertial frame of reference. These are also called as accelerated frames of reference. Such frames of reference can be represented by d square r by dt square is not equal to 0. And examples are a frame of reference attached to a giant wheel, or a frame of reference fixed on a freely falling elevator, a frame of reference attached to a car moving with a uniform speed and negotiating a curve. These are all examples of uniformly accelerating systems. In an uniformly accelerated systems, we here next we are going to check if a physical quantity or a physical law to an observer in a system accelerating at a rate a with respect to an inertial system. In this case, a dash is equal to a minus a, where a is the acceleration of the primed system as measured in the inertial system, and f dash is equal to ma dash, and ma this we can write as ma minus ma. A is the acceleration of the primed system. So this ma is the true force, where f is due to physical interactions. So f dash is equal to f minus ma, and we can write it as f is equal to f plus f fict is the fictitious force. So there are fictitious force when we are measuring with the accelerated primary system, accelerated frame of reference. So this fictitious force comes to action where f is equal to minus ma. The fictitious force in a uniformly accelerating systems, they behave like a constant gravitational force, and this fictitious force is a constant and it is proportional to the mass. As seen this in equation, it is constant and it is proportional to the mass. So there are force acting, there are fictitious force acting when an inertial frame of reference in the inertial frame systems, and there are three examples for such a fictitious force. One is apparent force of gravity. Apparent force of gravity is measured when a small weight of mass m hangs from a string in an automobile or a car which is accelerated at a rate a, capital A. Suppose this is accelerated at a acceleration of a, and what is the static angle of the string from the vertical, and what is its string, what is its tension? These are the questions we are going to solve here. We shall analyze the problem both in an inertial frame and in a frame accelerating with the curve. So inertial system, and system accelerating with the auto or the car. So here we are going to work out this. So in this example, a simple pendulum which carries a mass m is suspended from the roof of the car moving with an acceleration a. We want to find the acceleration a and the tension acting on this string. So our aim is to find the acceleration and also the tension acting on the string. We solved this problem both in inertial frame and in a frame accelerating with the car. So in an inertial frame, first let us look into the inertial frame. With respect to an inertial frame, the force acting on the pendulum are, one is gravity, mg, weight vertically down, and the tension T acting along the string up. Third one is the force experienced by the bob due to the acceleration of the car, F is equal to ma. So the theta is the angle made by the string with the vertical. Splitting T into two components, we are going to split the T into two components, T sine theta acting vertically up and T cos theta, it is acting horizontally. Since the pendulum is in equilibrium, the vertical component balance each other. So T cos theta is equal to, we can write T cos theta is equal to a weight mg, or T cos theta minus W is equal to 0. Similarly, the horizontal component also balance each other. So T sine theta is equal to force or ma. So we got two equations, T cos theta is equal to mg, T sine theta is equal to ma, weight or mg. So equating equation 1 and equation 2, if we divide equation 2 by equation 1, it can give tan theta is equal to ma by w, or you can get a by g. So we get a is equal to g tan theta, a is equal to g tan theta, and this from this g tan theta we can measure. If we know theta, acceleration of the car can be determined. Here the pendulum acts as an accelerometer. So squaring the equation 1, T cos theta is equal to this the equation 1, this is the T sin theta is equal to ma is the second equation. Squaring and adding the equations, these two equations, we can get T is equal to m into g square plus a square all raised to 1 by 2. So from a is equal to g tan theta, we can find value of a. If we find the value of a, we can find the value of T, tension on the string. This is in the case of inertial frame. If we come to a non-inertial frame, that frame is fixed in the car. So this is obviously it is a non-inertial frame. With respect to the this frame, the forces acting on this pendulum are, one is force due to the gravity acting vertically down, and another one is tension, and tension acting on the string. And here comes the fictitious force, as we discussed in the earlier slide. Fictitious forces come to action. Fictitious forces has to be taken in account in this case. So we have two horizontal the two, when we split the T tension into two components, they balance horizontal and vertical components of force separately. So we get T cos theta is equal to mg, T sin theta is equal to fictitious force, T sin theta minus F fictitious is equal to 0. So fictitious force is minus ma. So we can write these two equations as in the earlier case. We are getting two equations. One is one is t cos theta is equal to mg, and t sin theta is equal to ma. A is the acceleration of the car. So again we are getting the same equation for a here by equation dividing equation 2 by equation 1. We will get s equal to g tan theta. And finally, if we squaring and adding these two equations, we will get the same equation for tension. T is equal to m into g square plus a square all raised to 1 by 2. So if we know the a by measuring the theta, we can easily find out the tension on the string. So this is the example for apparent force of gravity. Next we have another example of cylinder. It is on an accelerating plank. Here also a cylinder of mass m is and radius capital R. It is rolls without slipping on a plank, moving with an acceleration capital A. So capital A is the acceleration of the plank. So we have to find the acceleration small a of this cylinder. This cylinder is having a mass capital M and a radius of capital R. Here we solve this. So we solve this problem with respect to a non-inertial frame. For this we fix a frame on the plank moving with an uniform acceleration capital A. Let small a be the acceleration of the cylinder with respect to an inertial frame, and a dash be the acceleration of the cylinder with respect to the non-inertial frame fixed to the plank. So we have an equation. We have an equation like this: a is equal to small a is equal to capital A, acceleration of the plank, plus a dash is the acceleration of the cylinder with respect to the non-inertial frame. So we have equation a is equal to a capital A plus a dash. Our aim to find a dash, and thus we will find the value of x a. So there are three forces acting on this cylinder. One is the force acting on the cylinder with respect to the frame fixed to the accelerating plank, are one force ma dash. It is acting in the forward direction, as well as the F fictitious, which is acting F fictitious force. It is acting in the opposite direction of the ma. So it is F fictitious can be written as minus ma. And third one is frictional force, that is also acting in the forward direction. So we have an equation of motion with respect to the frame fixed to the accelerating frame. So we can write the equation of motion F is equal to F minus F fictitious is equal to ma dash. We can write this as equation 1. And equation of torque experienced by the cylinder is equation Fr is equal to minus I alpha dash, where I is the moment of inertia of the cylinder and alpha dash is the angular acceleration of the cylinder. This cylinder rolls without slipping, so that we can write a dash is equal to R alpha dash, or alpha dash is equal to a dash by R. We can put this equation as 2. If we put the value of alpha dash in equation 2, we will get Fr is equal to minus I a dash by R, or F is equal to minus I a dash by R square. And if we put this force value of f small f in the equation 1, we will get if we put this value of f in the equation 1, we can write minus I a dash by r square minus f fictitious can be equated to m a dash, or minus f fictitious is equal to a dash can be taken out, m plus I by r square. So this is equation for fictitious force. Then we can find a dash. I'm wiping out here and writing the equation for a dash. A dash is equal to minus fictitious force from this equation, f fictitious by m plus I by r square, m plus r. The value in the bracket is coming into the denominator. So we know that f value of f fictitious force is nothing but ma. So we can write f fictitious can be given the value of ma, capital A, and I is I inertia of inertia is mr square. Since it is a cylinder, it is mr square by 2. So the a dash is equal to m a by m plus mr square by 2 r square is equal to minus 2 by 3a. So the value of a dash is got 2 by 3 minus 2 by 3a. We have our equation from the starting. In the starting we had an equation a is equal to a plus a dash. So this a is equal to a minus 2 by 3 a, which is equal to 1 by 3a. That's why we are getting a is equal to, here we got a is equal to 1 by 3a. So this is the example of cylinder on an accelerating plank. The next example is third example is a pendulum in an accelerating car. So the third example, pendulum in an accelerating car. For this, consider again the car and weight on the string as seen in the example 1, but now assume that the car is at rest with the weight hanging vertically. As you can see, the apparent vertical weight is there. The car is suddenly accelerate at a rate capital A. This problem is to find the maximum angle phi through which the weight swings. So phi is larger than the equilibrium position. This is larger than the equilibrium position due to the sudden acceleration. So in this system accelerating with a car, we can consider this bob behaves like a pendulum in gravitational field. So this phi can be phi 0 can be calculated as arctan of a by g, arctan of a by g, because we in the example 1 we had calculated a is equal to g tan theta, and from this we can find phi 0 as arctan of a by g, and this phi 0, this phi total maximum amplitude or the pendulum is initially at rest, so that it swings back and forth and amplitude phi 0 is the phi 0 is the amplitude about the apparent vertical direction. Therefore the total oscillation phi 0 is equal to 2 phi 0, and it is equal to 2 arc tan of A by G. This is the third example of pendulum in an accelerating car. So using this three examples, I conclude this uniformly accelerating systems or non-inertial frames of reference. For this for now, and if you have any doubts, you can contact me anytime. Soon I will post the other videos. Thank you.